Thanks. Okay, welcome students. Um, Last meeting, we didn't have any iClicker questions because of some kind of a software failure on my MacBook. But today, Caroline and I were just going through a procedure for using the desktop, the PC here installed in the lectern. So that's why we're a little slow starting this morning. We're going to do some clicking. Have your iClicker ready and your calculator. Roman numeral 1 is review questions. And I'll throw in some review questions every once in a while. By the way, homework 7.1, I announced it in lecture Tuesday, and a couple things about it. I forgot to put it on the homework list page until this morning. And so I think a few of you might have been caught napping with that. But in actuality, you can always go into the quizzes page and see all the homeworks right in there. So anyways, that's fixed. Also, with homework 7.1, it is basically a study tool. It's regular homework, and I want you to do it and get the points for it. But I set it up so that you, A, have more attempts, 6, that you can take, and B, the deadline is October 13th. That's the day of the next midterm at 9 a.m. So we'll do our midterm at noon on October 13th in this section, but you got to finish that by 9 a.m. So don't be caught napping. Hopefully you've gotten in some good attempts and crushed it. Another thing, I was talking to a student earlier today about, Dr. B, how can I get some more extra study to help me do better on my exams? And just so you know, and I know many of you would like to have extra work to do and eventually do well on your midterms and final. And what I normally say at this point in the semester is a couple, 3 things. First of all, try to get to SI, even if it's just for half an hour on Monday and half an hour on Wednesday, one of the Wednesday sessions. By the way, everybody can view and listen to the recorded online session, which is on Wednesdays in real time, live, 4:40 to 5:30 p.m. But Maria records that, right? And then, how do they get to can you give me the links? Send me the link, and because I do that with my online class, with my online office hours. So just send me the link. We'll set up a page for it. Actually, you already have an SI page. We'll put the links to the recordings there. Okay, and it'll work. It'll work good. Just send me the link. So you can always view that, and even though you are not able to participate, between 4:40 to 5:30 p.m. on Wednesdays, you can still go, at 11 p.m. when you get off work, you can go and review it and listen to everything they say and everything that Maria says and stuff. So hopefully that'll be good. Okay, that's 1. 2, try to come to either my office hours, 11 a.m. to 1 p.m. on Wednesdays, or to Darian's office hours, which are 1 p.m. to 2 p.m. on Mondays in the physical science building in the atrium. And those are valuable because of similar reasons. You're interacting with another human being, either me or Darian, about the material, and that helps you to think. And thinking and developing your ability to think about physical science is going to help you on exam day, to perform at a higher level, which is what you want to do. Okay, that's number 2. Number 3, either in office hours or SI or in class here, See if you can make friends with somebody and that you know is doing good, or hopefully you'll both be able to help each other out. A study partner or a study group. And I know that there's study groups happening. We had some study groups here before uh, exam one. What was it, room 374? I heard there was about 15 people in there. Did anybody go to that one in the library, room 374 or whatever it was that night? That must have been wild and woolly in there. But those kind of things help. And the reason it helps to go to something like that is because if you can find a classmate to study with, it'll be helpful. And if you can help your classmate with concept A and they can help you with concept B, then you both will be stronger. All right? So it's a good way to make friends and also to study and perform better on exams. All right. Now, before we get to the review questions in iClicker, I want to go over something that I updated a couple days ago. I forgot to mention it on Tuesday. And that's the rough schedule of topics and readings in web courses. It's a separate page. Here's the home page. And down there on the list of links, number 6, here it is. Rough schedule of topics and readings. Basically, if you click into there, you'll see for every week, Tuesday and Thursday lecture, a little description of the topics and the pages that you can read. So here's what it looks like for these past, from last week is week 5, and then this week is week 6, and then next week is week 7, and then week 8, you have lecture L15, and then lecture L16 is midterm exam 2. So you can look at that. And then over here on the fourth column over to the right is basically what chapter we're in or what chapter we're finishing. So we're in chapter 5 now on angular momentum. Next week we're going to be in chapter 6 on heat and thermal energy, and we're going to finish that in lecture 15. And so exam 2 is going to be a bear cat. You're going to have a lot of different kinds of calculations. Stopping time, stopping distance, thermal equilibrium, melting, heat, melt, heat. Some problems that are traditionally some of the most difficult of the semester you'll be hitting in exam 2. Now, so that's this rough schedule of readings and topics page. The exams are in yellow for midterms. They're in black with white lettering for the final. Also, I'll just remind you that the Twitter feed also contains cues, either a page or a chapter reference as I go. So when, although Caroline is going to be up here helping me with the clickers this morning, she's also, hopefully a little bit later, she'll start tweeting out notes into the Twitter stream as she usually does. And you put chapter and page numbers in there. Good. So that's to help you read. And I know a lot of you guys think in terms of studying ahead and keeping up with your reading and stuff like that. So this is something new that I've decided to do this semester to help you for that. Any questions about readings? Okay, let's keep going. I was looking through some of my old Keynote files from a few semesters back, and I saw this big one I have. This is a postage stamp. Deutsche Bundespost that's German for German Federal Postal Service. That's a stamp. Sir Isaac Newton stamp. 100, I don't know what that is. It can't be 100 marks or 100 euros. It's got to be 100 pennies or something like that. 100 cents. Anyways, this particular, if you look in that, see that equation in red in the upper left? Yeah. This one. Yeah, right there. Yeah, we were talking about that in office hours yesterday for a bit. So that's the form that we've used in the past. We've talked about that one. Notice behind there, there's a diagram of a prism and a rainbow over to the left. That's another thing that Sir Isaac Newton is famous for, figuring out refraction of light, which is what prisms do. If you have eyeglasses, they refract light. They bend light. And he's the guy that first figured out how those work. All right, clicker questions. Get your clicker ready. And we're going to run a question here in just a second. And these two questions, as I've mentioned before, they are designed to get you to think. You know, with that big gray blob of stuff at the top of your neck, encased inside this round object called a skull. Yeah, I want you to exercise that stuff. And so take notes on what we have here and think. Here's question 1. Go ahead and start. And, go ahead and close that. Okay, go ahead and, so practice exercise. How do you know this is a pop-up? And you have to really think carefully about this. Can you click the little histogram icon up there? The bar chart icon, yeah. I'll show what people are voting for. Yeah, see, this is different from last hour because of our little unfortunate event. See how that goes? Is that nice? Yeah. Yeah, how do you know it's a pop-up? Which set of facts? See, everything in there is true, but which is the set of statements that lock this in as a pop-up for sure? That's a little bit more difficult of an idea. Twenty seconds. Now, unfortunately, since this is on the PC, they won't be able to see the bar chart, but I don't know, maybe we can figure out some way to do this later. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, stop it. All right. Now, it looks like a bunch of you, 65% of you voted correctly for option C. Make a note of that, and I hope you've jotted down the other 5 options in your notes. You should do that now if you haven't, because I want to talk about both, all these different options. Option A is incorrect. Vix is equal to 0. The x component of the initial velocity is 0. That's what this means up here in parentheses here. I've written it as a 2-dimensional vector with, in parentheses with a comma separating the 2 components. The initial velocity component in the x direction actually is 0.00 meters per second, but that doesn't guarantee you have a pop-up. So let me ask you a question. Let's raise your hand if you can think of an idea. What's another possible alternative to a pop-up, but yet Vix is equal to 0? What do you think a possible, think about it. Raise your hand if you have an idea. Okay, I see your hand. Red shirt. Free fall. Good. Free fall. It could be in free fall, straight down from the top of the library. Okay, something else. How could you get, okay, another red shirt over here. Could be at rest. All right. VIY equals 0. In that case, it's not doing jack. Okay. Another one. Go ahead. Well, yeah, he misses it, then it just, yeah. It's, yeah, so that's at rest. Yeah, so the guy, it's on a tee, the guy misses it, and that's basically at rest. You know, can people do that? I mean, do you miss when you're playing t-ball? I've never played t-ball. I mean, I guess little shrimpy kids do, but anyways. So I guess, yeah, technically it is possible. Also, what if VIY is negatory? And that would be a free fall, or it hits the ball straight down and it hits home plate. You know? So now, option B, VIY, that's true. 20.0 meters per second, yeah. But now let me ask you another, in a show of hands, think. Remember, think. That's what I want you to do. Think. What possible alternative could there be, some other motion in which VIY is equal to 0, or excuse me, VIY is equal to 20.0, and VIX is not 0.00. What possible variation? I mean, this is a pop-up, but what other possible thing could option B include? Yes?
Hitting the ball out the field.
Okay, there you go. The one possible exception is hitting the ball towards the outfield. Okay? If VIX is positive, then you're heading towards the outfield, over second base. Or if VIX is negative, then you've hit it, it's going upward, but it's kind of cutting behind you. So like when they foul off a pitch into the screen, into the backstop, that'd be VIY or VIX equals like -3 meters per second, something like that. So yeah, that's possible. So option B is out. Now, option C is you've got to have both. So make a note to yourself, option A is necessary for a pop-up, but not sufficient. Option C is necessary and sufficient. Option C is the lock. Option A is necessary, but it's not a lock. It's not sufficient to lock in the motion as a pop-up. Option B, necessary, it's got to be going up to be a pop-up, but it's not sufficient by itself. And for the same reason, option D and option E are also, they're true and stuff, but they're not sufficient. They don't, guarantee a pop-up. Only option C does that. And my last comment to you about this question is simply this, that this question is kind of deluxe in that to answer this question, you have to analyze the velocity, the initial velocity components, VIX and VIY. All right, so make a note of that. And that's a kind of a higher order cognitive process, analyzing, analysis. Yeah, you break apart the motion into initial vertical and initial horizontal, and then you make your decision based on looking at both of them at the same time. So that's kind of an analytical move. And it's an example of higher level thinking that if you can do that on exams, you're going to perform a little bit better. All right, let's do another question. And this is another thought question. All right, pop up. Initial velocity is vertical component 20.0. What's the hang time? How long does it remain in the air? Go ahead and start. Think that one over. And definitely talk to your neighbor. You're free to blab and gab as much as you like. This is pretty easy. I could probably do it myself. What do you think? Oh, I got something to ask you at the end of class. What's your schedule like on Fridays? Crazy?
No.
Not too bad?
No, I only have one class.
When is it?
2:30 to 3:20.
Hmm. Then you're done for the day?
Mm-hmm.
This is good. I love being able to see the students interact and talk things over. What's that?
Somebody was going like, they were like motioning the
Yeah.
question.
Yeah. That's good. See this guy back here? He's going like this. And, you got it? You think? Yeah. And then there's guys in the front row sitting by themselves. Nobody to talk to. Usually somebody's over there though, right? Gosh, they ditched you. See, there's Brian and Nick.
Mm-hmm.
Guys talking it over, that's good. And what's your name?
My name?
Yeah.
Nick.
Nick? And you're Nick.
I'm also Nick.
So Nick in front is listening in on both of you guys back. Hopefully you guys can get the right answer. It's good. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Boy, you clicked that. Caroline's pretty mean. She clicks it right at 0. I usually give you guys, I say 0 and then I give you another extra second or two usually. But Caroline, she's pretty tough. Let me look at, 55% of you voted for B and 36% of you voted for A and a sprinkling of people voted for C and D. The answer is B. Now, I'm going to give you a couple different ways to think about it. All right? Now, if you can contain your excitement. The first way I'm going to discuss it with you is informally and so that you can kind of make a mental estimate of the hang time. And the first thing I'd like to point out to you in regard to that is that on the way up, the baseball loses all of its upward speed at the rate of 9.8 meters per second. In other words, it loses 9.8 meters per second of upward speed for every second of upward motion. All right, so after 1 second, it starts out with 20, and after 1 second, whoops, I'm down 9.8. Still has 10.2. So it's still going up. After another second, let's see, 10.2 minus 9.8 is 0.4. So after 2 full seconds, it's still kind of going upward, but slowed down to 0.4 meters per second. So the rise time, or the amount of time it takes to get all the way to the top of its motion to apogee, is about 2 seconds. And the total hang time is double that. Because, as I've mentioned in other lectures, this situation is a case of the Lord giveth and the Lord taketh away. All right? We're taking a thing away on the way up for 2 point something seconds, and we're giving a thing back on the way back down for another 2 point something seconds. All right? Now, that being the case, you don't need 3 seconds to lose all your speed. You just need 2.0 something. Now, we're going to calculate that in just a minute. And so this is the second way. Actually calculate it out. How many people, raise your hand if you actually calculated it. Anybody? Bueller? Oh, good. A bunch of you guys calculated it out. Good. Now, check your work. And for those of you that didn't calculate it out, jot it down. Here's the equation you start with. The change in the speed for accelerated motion, in this case, vertical free fall. So the change in the y component of the velocity, delta v subscript y, is equal to g delta t. Now, in this g, when I put the numbers in for it, it's going to be negative 9.8. All right? Now, this diagram over here, by the way, you guys, this over here is another way to write down a vector with the vector measurements recorded. It's called a column vector, and this one I've recorded it in 3 dimensions. So the x coordinate is on top, or the x component, I should say, 0.00 meters per second. And then the y component is in the middle, 20.00 meters per second. And then I threw in the y component for free. It's 0. So it's a straight pop-up. So you only have y. All right. And if it was a base hit, toward left field, you'd have a little bit of y, or a little bit of z, and a little bit of x. If it was straight out to center field, you'd have some x, but you wouldn't have any z down here. Right? So, anyways, so this is called a column vector. Here's the vector itself, as represented as an arrow. Now, this formula, v subscript y equals g delta t, that's where you start. And my next move is to get delta t, the rise time, by itself. And I'm going to calculate the rise time. I'll show you how to calculate the hang time using this same equation. But first of all, to get delta t by itself, in this case the rise time, I better get g over to the other side. Right? I divide both sides by g. That clears g from the right side. Now I just have delta t. And it puts g in the denominator on the left side. So I have delta v subscript y divided by g. And now we can put in the numbers and get delta t itself. Okay, delta v on top. Okay, that's v2 minus v1. Now this is for the rise time. So my v1 is 20, and my final v, if all I want to know is how much time it takes to rise all the way to the top, my final v, v2, is 0. Because at the very top, it stops. Okay, so in this case, to figure out the rise time, 0 meters per second minus initial 20 meters per second. And then g is down the bottom. And notice that the minus signs here work out nicely. I have negative divided by negative. So my delta t is positive, which is good. And if you actually calculate it out, it's 2.04. Now let me make a note to you that calculating the rise time like this and then doubling it is perfectly fine. But this yellow box and the red box before that showed you how to think of it in terms of making a mental estimate, doing mental arithmetic. Now, I want to make a comment about that. So if you want to do a side note, mental arithmetic, and thinking about the meaning of G, for every second of upward motion, you lose 9.8. Now, that's almost 10. So a rough rule of thumb is for every 10 meters per second of upward speed that you have, whether it's 20 or 200, divide that by 10, and that's the number of seconds. Because every 10 meter per second, roughly, requires a second of gravity, of gravity's effect. Okay? Now, if you want to calculate it exactly, you do it like this over here with the equations. But if you're just trying to get a rough estimate, every 10 meters per second of upward speed, give it a second. And then, so if you started, so go ahead and make an example. Side note number 2. If initial upward velocity, VIY, was 30 meters per second, 30 divided by 10, 3. 3 seconds for the rise time, approximately. All right? It's a good ballpark estimate. And my question itself, my multiple choice here, was just, in terms of whole numbers of seconds. So 3 seconds. I would have had to have 3 seconds on there, and that would have sufficed. All right? 200, so side note number 3, VIY equals 200 meters per second. That's about 400 something, 450 miles an hour. It's going pretty fast. So if you launch something straight up, a pop-up at 450 miles an hour, like with a gun or something like that, or a cannon that goes straight up, 450 miles an hour, it's pretty fast. And so let's see, 200 meters per second, 200, so 1 second, you're down to 190, 180, 170, 160, 150, 20 seconds. 20 seconds up, 20 seconds on the way down. That's a lot of hang time. Side note number 4. Yes, you can calculate delta t for the entire hang time if you remember that the final speed, so you can figure out delta t for the hang time if you remember or know how to write down, instead of a 0 here in this numerator, a different number for the final speed. When this thing gets back down to the ground, just before impact, what is its velocity? It's not 20, it's negative 20, or 20 meters per second downward. Right? So if you wanted to do rise time, you'd have a negative 20, or excuse me, if you wanted to do full hang time, you'd have negative 20 here instead of 0, and you'd have subtract 20 here, so negative 20 minus 20, negative 40, divided by negative 9.8, and you're still at about 4.08 seconds. And that gives you the answer. All right? Now, this is a review question. Let me pause for just a second and see if you have any more questions about it. Okay, let's keep going. I want to talk some more about angular momentum. And what we're going to talk about is the ice skater effect today. This is a diagram from page 74. We'll talk more about this in a minute. I want to show you some videos in YouTube. Can you get the Google Chrome screen? We're going to switch over for just a moment. We're going to switch over. Yeah, you can close that. You can close that. Okay. We're going to switch over. I'm going to pause my podcast here for just a minute. We're going to look at some videos on YouTube. What you want to do is go to the same website if you want to go and study those videos some more. The same website where we have lecture YouTubes. Just go to the one that says Angular Momentum. You can look at them. There's all kinds of stuff in there. Now, on this, on that note, let me just add a few more ideas, again, in relation to this diagram from the textbook. You know, we've been thinking about objects that we've treated as, you know, as if they're a baseball. You know, if you were to throw an extended object like a straight edge here or a board, it would, if you don't throw it right, it'll spin as it moves. And a baseball we don't think of as an object that moves any differently because of its spin state. So we just think of it as, you know, something that goes from point A to point B. If you take a real object like a board in this diagram, and so for instance, if you get this board moving with force F2 instead of force F1 in the diagram, it will move towards point B, but it will also spin. If you only use force F1, it'll move straight towards point B because you're pushing through the center of mass. Now, one of the things that, if you've ever played tackle football, they tell you to tackle a guy right in the guts, you know. I mean, if you can, because that's the center of mass. And that'll stop him fastest. And that's like pushing here with force F1 through the center of mass, point C. But if you do that, it's just F equals ma. But if you push through point A, in other words, using force F2, you also have to take into account the torque effects. All right, so make a note of that. F equals ma and the torque effects, you've got two independent, they're not independent motions, but they're independent parts of the motion. All right, the spin is independent of the F equals ma point A to point B motion. All right, now here's an example of that. This is an overhead view of a wrench. Now, a wrench is an irregularly shaped object. This little black square that you see here, right here where my cursor is, in this leftmost image of the wrench, it's tilted about 20 degrees to the left. And this black square here, they painted that on the wrench at its center of mass. And you can read in the textbook how to figure out the center of mass of an object. And if you look at this strobe photo, you know, this is like every 10th of a second or something. And it's an overhead view, so it's on a frictionless table or a relatively frictionless table. And they threw it, or they moved it, but not with a force through the center of mass. They moved it with a force a few centimeters away from the center of mass, and because of that, it's spinning. But look at the position of the center of mass. See, here's the black square here. Here it is again. And matter of fact, I put a bunch of bluish diamonds outlined in white to put down over each of those black squares so that a little more visible for you. Here they are. Look at that. Look how regularly they're spaced. All right? The center of mass is just going delta x equals v delta t. Make a note of that. In this overhead view, the strobe photo, delta x is equal to v delta t, and v is not changing. You know, not changing very much anyways. It's pretty low friction. And we're in an overhead view. So this is a black low friction tabletop that we're looking at, and somebody just kind of skittered the wrench across the tabletop, and then they got the strobe photos. All right. Now, you can tell that they didn't push at that very center of mass where the black dot was, or the black square, or where my blue diamonds are, because it's spinning. And so you cannot say that this is a simple motion like a baseball. If you do this with a baseball, the baseball just goes across the room. It doesn't look any different. This one, yeah, you've got that spinning motion. And it keeps spinning at the same rate. And a matter of fact, if you think about it here, this first blue diamond, let's see, 1 flash, 2 flash, 3 flashes, 4 flashes, 5 flashes, 6 flashes, 7 flashes later, the wrench is 180 degrees away from its start. All right? Raise your hand. I'd like a show of hands. Raise your hand if you ride a motorcycle. Bueller? Anyone? Where? Oh, okay. One person. Raise your hand if you've ever ridden a motorcycle. Okay, that's a little bit more. Now, for those of you that ride motorcycles, have you ever done this? Whoa, look at that guy. Dog. Now here, that's a photo, that's a strobe photo. Here's a strobe photo. And this white arc, so I don't know if you can make a sketch of this, but definitely make a note. This guy has launched the way a motorcyclist would do this is going up a ramp and taking a ramp at good speed and then landing. And look at this. He lands right over here perfectly. Oh, my goodness. And he did a backflip. Can you see that? Can you imagine? Oh, my God. I would not want to try this. I get sick even looking at this. But this guy he's basically following the same path as a baseball. I mean, his center of mass is. That's where the white curve is. But he is spinning. Because I don't know how they would do that. They what? Just as they go off the ramp. Right. So he pulls a wheelie a little bit, just as he goes off the ramp. And then he spins, and if he doesn't do it right, man, he's going to break every bone in his body. But this guy did it right, and he looks like he landed pretty good. And there's another guy. Look at this. I didn't notice this. Here's another couple guys down here. Man, I tell you what, you'd have to pay me a lot of money to do that. Have you ever done that? Yeah. Good. Don't do it. Don't do this at home. All right. Now, I want to give you a few specs on moment of inertia. The moment of inertia is the rotational analog of mass. You'll have some homework with this formula. And it'll be pretty cinchy. You'll be adding up moment of inertia, mr squared, for a bunch of different masses. And then kind of asking questions about it. But in the textbook, these two diagrams are in there, the two dumbbells. And one of them is 45 centimeters across, and the other one is 60 centimeters across. So for the way this works is you think about the moment of inertia as, for this dumbbell over here, you take every gram of mass, every gram of steel, so like a fraction of a cubic centimeter of steel, and just calculate 1 gram for m, and then r squared for wherever it is, and then go to the next gram and do 1 gram times r squared for that gram, and do it for all the zillions of grams in each of these things. Now, in this dumbbell here, the one on the left, the lower left, most of the grams are at a r of 22.5 because it's 45 centimeters across. All right? This one over here, most of the mass is 30 and 30. 30 meters left, 30 centimeters left, 30 centimeters right. So r squared is bigger. And this one on the right, the dumbbell on the left, the dumbbell on the right will be harder to spin. Because it's got his arm, it's like Richard and Shalissa with the arms out. All right? And this one over here, the one on the lower right, the one on the lower left, the 45 centimeter dumbbell, that one's going to be easier to spin because that's like having your arms in on those U-tubes. All right. Capital L equals I omega. That's the angular momentum. Angular momentum, if you're on a good bearing, or if like the motorcyclist Morgan, if there's not much air resistance, angular momentum will be conserved. So the left-hand side has got to stay the same number. And if I goes up, omega goes down. If I goes down, omega goes up. And that's what you saw in those U-tubes. Question?
I thought that was spin angular momentum.
It is.
Well, what's orbital angular?
MRV. We're going to mostly, for these ones, we're talking about spin angular momentum. Notice anybody in this picture? Stand up, Caroline. It's Mighty Mighty Caroline. This was her SSG a couple semesters ago. And just to remind you, exam 2 is coming up a couple weeks, 2 Thursdays from now. And if you can get your exam average up to 90%, you can maybe run an SSG. All right, let's dismiss early. And homework 8 will be activated tonight. I'll see you on Tuesday. Good job today, you guys.